Sven Lidin, member of Nobel Committee for Chemistry, that has just awarded a discovery of quasicrystals. What are quasicrystals, actually?
Quasicrystals are perfectly ordered materials that never repeat themselves. And this was an absolutely unexpected discovery made by Dan Shechtman in 1982. It has taken a very long time for this discovery to be accepted by the entire scientific community. But today, quasicrystals constitute an entire area of science all by itself, spanning over chemistry, physics, mathematics, and material science.
And they are very special. How?
They are very special because of the atomic ordering in quasicrystals. In fact, the atomic ordering is so special that it took 25 years just to find out where the atoms are. And today, finding out where atoms are in a solid-state material is really a routine task. But in quasicrystals, it turned out to be a real challenge for scientists of all branches. They're also very special because they have special properties. They have very low coefficients of friction. They are non-stick materials which nothing seems to like to grow on. They are hard, they are brittle, and they conduct electricity and heat very poorly. And these properties make them interesting and useful as well. But of course, a lot of this development will be in the future. What we have seen today is that the combination of a low thermal conductivity and a high chemical resistance, a resistance to adsorption, makes them very interesting as coating materials in environments in extreme environments, such as on turbine blades, for example.
So can you produce those in some artificial way?
Most quasicrystals are produced artificially. The only known natural quasicrystals are a mineral from eastern Russia. It is only known in microscopic quantities. The first quasicrystals were made in the laboratory by Dan Shechtman, and most quasicrystals have been made this way. Many quasicrystals are made by rapidly cooling metal melts. By taking a metal melt and squirting it onto a cooled wheel that rotates at a high speed, giving cooling rates of 1,000,000 degrees per second. And this preserves some of the liquid properties of the metal. And this is used in many applications. If you cool even quicker, you will get a metallic glass, and these have been known for a long time.
And this discovery has led to a paradigm shift in chemistry, as I understand, materials chemistry. What was believed before?
Well, before, the idea of having a crystal that wasn't periodic was utterly unheard of. And our entire theory for the properties of solid-state materials has been built on the assumption that everything is periodic. Electricity, magnetism, all these well-known properties are treated for periodic systems. When quasicrystals came about, we had no idea of how to treat these systems in terms of their physical properties. It turns out that they do have very special properties. They're not out of this world. They have similarities to existing systems, but they are more extreme in many respects. For example, the thermal conductivity, the propensity to carry heat is much, much lower in quasicrystals than in normal crystals. It's actually lower than in most glasses.
So somehow the chemical and the electrical and the heat properties, they relate to a geometry of the material.
Oh, they're very much linked. And this has to do with the wave nature of most transport phenomena in matter. We can describe most transport phenomena as waves propagating through matter. And waves are periodic things. And these waves break down in quasicrystals, and this leads to very different transport properties. And this has baffled science for a long time, but we now understand it in a much better way, and we are much better equipped to tackle new phenomena, because embracing this paradigm shift has, I think, made us a little bit more humble about what we know and what we don't know. There's a big world out there that we have very little understanding of yet.
Actually, in two-dimensional systems, in a flat surface, this was a question of geometry and mathematics for a very long time, since the ancient Greece, I would say.
Sorry. Oh, yes, indeed. And it's quite interesting that the flat quasicrystals, the two-dimensional quasicrystals, they're understandable in terms of the Penrose tilings. I have a couple of Penrose tile parts here. These are like jigsaw puzzle pieces that can be fitted together only according to certain rules. And generating a Penrose pattern gives us patterns that we recognize from other parts of...
You can show it for us.
Let's see. So these pieces may be put together in different ways. Now, this is not allowed. There are little markings on these telling us how we're allowed to put them together. If we put them together according to these rules force aperiodicity, a pattern that never repeats itself. And we can find such patterns in old Arabic murals from the medieval times. We can find these basic shapes, we can find in Kepler's writings, and we can find them throughout history where artists and applied geometers have tried to make fivefold symmetry work. And they had come very close, but it was not until the work of Roger Penrose in 1974 that there was rigorous proof that aperiodicity could be forced from a tiling pattern. Still, with that knowledge, the world was completely unprepared for the discovery of Daniel Shechtman that such aperiodic beasts actually exist also in solid matter.
And even him couldn't believe it from the beginning in 1982 when he saw it.
No, absolutely clear. From his notebook, he makes a short note in his laboratory notebook, and it's followed by 3 question marks. He was well trained. He completely understood that what he saw was forbidden, and yet he saw it. And to his great credit, he realized that what he saw was correct, and what he had learned was wrong. And this, I think, is a great example of the way science should be conducted. We have to build on prior experience, but we must question it at all stages. And that's what he did.
Thank you very much, Sven Lidin.
Thank you.